Welcome to Unit 3. So Unit 3 is all about trigonometric equations and identities. So we'll start with equations as like the first couple lessons that we see. So lessons 1 and 2 will and even lesson 3 will emphasize solving equations involving trigonometric functions. So sine, cos, tan, and their inverse functions, cosecant, secant, and cotangent. When we get to lessons 4 and 5, we're going to start talking about what's called identities, and that's going to be some new language for you. So just kind of be prepared. We are moving into some new realm, but we're going to try and start with something that's a little bit more approachable, a little bit more familiar, so that you can kind of ease into it. So lesson 1, as you can see by the title, is all about solving trigonometric equations graphically. So this is a skill you have from Unit 1. And we're going to be bringing it back a little bit for this first lesson, which means it's going to be nice and quick, hopefully, if I stop talking to you about what this unit's about and I start with the lesson. So here we go. So we can always go back to our graphs, and sine is our default because that's kind of what we always start with. So we know that our plain old parent function sine graph starts at 0, max is at 1, minimum's at -1, and it takes 2 pi to complete that whole period. So how does this graph relate to the equation sine theta equals 0? Well, we see that sine theta equals 0, so our output is 0, or our y value is equal to 0, essentially, whenever our graph is crossing the x-axis. So we get multiple solutions, and this is probably the first time you're really coming across that idea that we can have multiple solutions to the same equation. So if we were to solve this, we would see that theta could be 0, it could be pi, it could be 2 pi, it could be 3 pi. It could also be negative pi, it could be negative 2 pi, it could be negative 3 pi. So we say theta equals pi times n, where n is an element of the integers. And you'll see me using k instead of n, just kind of as a different number to use. It doesn't matter which one you choose, I will accept both. The main thing is that we establish that n is any integer, so a positive or negative whole number, or 0 is what that includes. And again, you'll also see me using the symbol z for integers, and I or z are both perfectly okay, but make sure it is an obvious capital I, because otherwise it might look like a 1, it might look like an L, and then things start to get confusing. So really emphasize that capital I, or you can use the Z. And I even sometimes do that with my I, where I would like double cross one side of it. I prefer Z. Okay, so all of these solutions are the same as the zeros, or x-intercepts of the graph of y equals sine theta. So determine the zeros of the function y equals cosine theta minus 1. Well, knowing what we know about transformations, I can tell you that my d value is -1. So that means that my midline is down 1. I have no a value, which means that my maximum and minimum are going to be 1 away from my midline. So instead of being at 1 and -1, my max is going to be at 0, and my minimum is going to be at -2. I've got no shift, no b value, so no change in period, which means that my period is 2 pi, and so these are all things that I can work with. From here, I'm going to acknowledge cosine also starts at a max. All of this is going to help me draw my graph. So I'm going to start at my maximum, which is 0. I'm going to add my scale in horizontally as well. Make sure you always label your scale, which I haven't done yet. This is -1. If I had one, +1. And pi over 2. Okay, and if it helps, to kind of sketch in that midline. Do that. Okay, and then I'll draw my graph. So maximum, midline, minimum, midline, maximum. And again, we're coming back to that original starting point, so we can restart the cycle at 2 pi. And I would keep going in this way. And then we sketch in our curve. And it would look something like this. Now I can determine the zeros. They're very straightforward because it's whenever my graph hits my x-axis. So here, here, and here. So 0, 2 pi, 4 pi. And we could assume that this is going to repeat. So when I go to say that my zeros in my function, I could say at theta, because that is my horizontal axis, my vertical is y, equals, in this case I would say 2 pi because that's how often it's recurring. That's like the period for my zeros. But then I would multiply it by k. So you can write it like this. You could write it as 2k pi. You could write it as k 2 pi. All of those are acceptable. Okay, the key thing is to have that statement that k, or n if you wanted to use n, is an element of the integers. And acknowledging that this is my general solution for all zeros, not within a specific domain. For any zero, for infinity is my domain. Positive and negative. Okay. So going to this equation, we've got cos theta equals 1. Explain how the two solutions are related. After we find the general solution for cos theta equals 1. Well, let's have a look. Well, we could graph cos theta, in which case we'd need to my max and min are just going to be my generic graph. Oops, too close. Again, always making that effort to keep my scale consistent. Starting at a maximum, midpoint, minimum, midpoint. There's no stretch or compression because we're just talking about cosine, which is my parent function. So these points are well known to us by now, or a good review of Unit 1. Okay, so once I've graphed my y equals cos theta function, I'm solving for when cos theta equals positive 1. Well, that's here, here, and here. And again, we see that's happening at 0, 2 pi, and 4 pi. Again, sorry, I didn't label my scale there. So what you might notice is that these actually end up being that this happens at theta equals 2 pi k, where k is an element of the integers. So our solutions are exactly the same, even though we're looking at kind of two different statements. So we've got cos theta equals 1 versus cos theta minus 1. And what's happening here is like, well, we're basically saying the same thing. If we had rearranged this and said y equals 0, and moved the 1 over, we would get this equation here. So that's kind of how they end up comparing. So by being able to solve for theta, we're basically looking for specific points on our graph. So we can solve it graphically, or we can solve it algebraically. Our second example, and our last example of this lesson, looks at solving for sine 3x equals 0 over the domain of 0 is less than or equal to x, which is less than 2 pi. Given the roots to the nearest hundredth. Okay, determine the general solution of the equation. So we can start by graphing. A couple things that we're going to note, sorry for zooming out, we'll zoom back in, is that this is my b value. And remember that that means that my period is going to be 2 pi over 3. Or we can expect, in terms of frequency, we can expect 3 whole periods within 2 pi. So what does that look like when we go to graph it? Well, we double check there's no c value, no d value, no a value, so none of those other changes are happening. So I can still work with my usual parameters of maximum 1, minimum -1. Okay, and I'm still gonna draw out I'm only gonna draw out to 2 pi here because I don't need to go any further. So halfway would be pi. And because I'm dealing with a denominator of 3 in my period, I'm going to subdivide this into like 6. Just so that I can have those halfway marks. So I would expect 6 pi over 6 would get me to here. So I'm going to have 1 pi over 6, 2 pi over 6, 3 pi over 6. Okay, I'm trying to subdivide it evenly again. And so you can adjust things as you need. Looks like I should move over a little bit. This halfway mark just doesn't look quite right. So we can tweak it as needed. Sine starts at 0. We didn't do a reflection. We didn't move our midline, so all of that's good. But I know that by the time I get to 2 pi over 3, remember this is pi over 6, so 2 pi over 3 is here. I should be returning back to my original function. So halfway, sine goes to a maximum, halfway, minimum, and that would be my function. I'm going to repeat this until I get to 2 pi, because that was the domain that I was given. I'm not actually going to show it at 2 pi, strictly because then I would be going outside of the domain. So again, consciously making sure that this curve looks like a sine curve. You can really tell when my scale's kind of out of whack right here. You could even draw it there and then just make it a hole instead of a full point. So now that I've graphed sine of 3x equals y, basically. So looking again, this would be y, and this would be x in this case, not theta. I'm going to look at when does it equal 0? Well, it equals 0 here, 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 not here. And so how I would list that in terms of my whole solution, I would say x equals, I could list each individual one. pi over 3, not including 2 pi because it's not included in the domain. Okay, but that would be my answer to A. Answer to B, my general solution for the equation. If I didn't have that restriction on the domain, and that's the key thing, then I would state that x equals pi over 3k, or k times 3 times pi over 3. And again, I would state k as an element of the integers. If I wanted to still restrict my domain, I would just state exactly this. Or I could state the values for k. So k could be 0, 1, 2, 3, 4, or 5. So 0 less than or equal to k less than 6. And so I could list it like that. Or I could say less than or equal to 5, since I know that that's my cap. Okay, so that would be the domain to stay within my domain of my original question. If I was asked for a general solution, though, usually I'm talking no restricted domain. So I wouldn't necessarily need this. So I'll see if I can find a good worksheet that goes along with this lesson, but for the most part, this is just to give you a flavor for where these questions are coming from, and lesson 2 is going to give you the meat of what we're trying to do in terms of solving equations algebraically, which is the goal in this particular unit. So you've got the visual representation. You can always default back to it. There's nothing wrong with that, but we are going to try and use some algebra in the next lesson. As always, please ask questions for clarification. Let me know if there's a mistake in my videos, and the next lesson should be up soon.